Also, I guess it's on the title of the talk, right?
So the old title was How Constructive is Gödel's Dialectica Translation? And then for some reason I changed my mind and decided to call it Gödel's Footnote.
Okay.
But the two titles are equal value. It's the same.
Okay, good. Okay.
Yeah. Thank you very much for having me here. Thanks to Fedor for the invitation and to Giovanni for putting together the seminar. Yeah, I'm Stephen Mackereth. I'm a postdoc in the Society of Fellows and Department of Philosophy at Dartmouth College. The topic which I would like to discuss today is, somehow this question of how constructive is Gödel's Dialectica translation. So I will not assume that everybody has seen the Dialectica translation before. I'll try to say just a little bit about it. And actually, as we'll see, in some sense, the question is not really about the translation itself, but about the theory into which Gödel wants to translate Hating arithmetic. So let me get started. Gödel's Dialectica translation is an interpretation of Hating arithmetic, that is intuitionistic first-order arithmetic, in a theory T of what Gödel calls computable functions of finite type. Nowadays, we might say primitive recursive functionals of finite type. So Gödel made several contributions to intuitionism and constructive mathematics. The dialectic translation is some kind of interpretation of Hating arithmetic in this new theory T that Gödel produces. And Gödel has also given a negative translation of piano arithmetic and Hating arithmetic. This will show up at some point as well. So just to be aware that there are two different translations that you might think of. And actually, here's a third translation. There's a modal logical interpretation that he gives of intuitionistic logic, but I won't say so much about this. So Gödel was very interested in the foundations of constructive mathematics and in the relationship between constructive and classical mathematics. And nowadays, this Dialectica translation is quite famous for its applications in proof mining and in other parts of proof theory. Gödel originally intended the translation as a foundational reduction of Hating arithmetic to a more constructive theory. He thinks that T is more constructive than HA. Why? It is because T is supposed to be a quantifier-free theory in which all the primitive notions are decidable. So I'll say a bit more about why this is supposed to be more constructive and why one might desire such a reduction. This is how Gödel envisioned it. So there's supposed to be a philosophical and foundational move here. Gödel's foundational claims, however, have not been very well received. So there is an objection, the circularity objection, raised by Tate, Troelstra, Ferreira, seemingly every commentator on this matter. The objection is that Gödel's theory T, despite appearances, is actually not quantifier-free, because if you unpack the definitions occurring in T, you'll see that somehow quantificational logic is tacitly presupposed in explaining the notion of computable function of finite type that Gödel is using. So formally, T looks like a quantifier-free calculus, but if you want to explain what it really means, then you'll see that quantificational logic pops right back out, so that the quantificational logic has only been hidden, but not really removed. This would, of course, completely destroy the philosophical significance of Gödel's reduction. It wouldn't really be a reduction.
Right, so I don't know, do you plan at some point to remind people what is system T and dialectic interpretation? Because I'm not sure that it's full value.
Yeah, so, sorry, I will define T in detail later in the talk. I was not planning to write down all the clauses of dialectic.
Oh, yeah, I love it. No, but it's some kind of explanation what doesn't, right? So,
yeah, well, maybe I can say a few words now about how this translation is supposed to work. At least I want to say, in what sense is this an interpretation? If I'm interpreting a quantificational theory and a quantifier-free theory, this cannot be an interpretation in the ordinary sense, because that is defined when you have two quantificational theories. So in some sense, what Gödel is doing here, the dialectical translation, you can take any formula in the language of arithmetic. Gödel has this way of putting each formula into a kind of normal form. So you can think of the dialectical translation of this formula as being something of this. Now, I have quantifiers here. So this is not a formula of t. The quantifier free part is a formula of t. And this normal form is almost logically equivalent to the original formula. It's logically equivalent in the sense that you can prove this equivalence with, say, classical logic plus axiom of choice. Somehow there is an analogy here with Skolem normal form, where you say there exist Skolem functions such that blah blah blah, and the Skolem normal form is almost equivalent to a little bit of axiom of choice with the original thing. So this is somehow very closely connected in meaning with the original formula. And this is true for any arithmetical formula. In the particular case where Heyting arithmetic proves this formula A, then system T can prove a special case of the normal form. So if Heyting arithmetic proves A, then T will prove something like this. And I'm suppressing. So suppose we have no free variables. Suppose A is a sentence, just to keep things simple.
I guess so, right?
You can say constants or terms. The way that Gödel sets it up, he has zillions of new constants, but you could say closed terms if you prefer. Yeah. Yeah.
Oh, I remember the
Yeah. So this is somehow the general picture. What these formulas of T look like, we'll sort of come to later. Yeah.
No, I guess kind of nothing because pure just responds to a proof, right? So while what was the first part of translation is syntactical translation, the level of formulas, right? So you kind of from a formula A, you construct formula AD. So your second translation actually Q is a function of HA proof.
Right. So you can extract these witnessing constants very easily, any particular proof in HA. If you give me various different proofs of this theorem A, then I might get different witnessing constants. So indeed, somehow the constants somehow.
Yes. So you can actually define, at least give some amount of difference so that people who don't remember like details of what system T is and what dialectic interpretations will be able to follow what you're saying, because at this point I have very much doubt these people.
Yeah, so all of the definitions are going to come on page 2 and 3. I really will define T in scrupulous detail, but my plan was to give a bit of philosophical motivation first. Yeah.
On account of the philosophical motivation, so what is the critique of HA at the first place? What is the non-constructive part of HA?
Yeah, this also I was intending to come to, but let me just say it now. Basically, for Gödel, the essence of constructivity is avoiding non-constructive existence proofs. So the question is, does HA really do this? And here, Gödel's basic worry or cause for doubt is that the negative translation goes too easily. The non-constructive existence theorems in Peano arithmetic somehow get very easily renamed or relabeled as not for all not theorems in HA. And the fact that this translation goes so easily might make you wonder whether some non-constructive element is crept into HA. Furthermore, if you just look at the existential theorems of Heyting arithmetic, then things look quite good, because then you have this existence property. That HA can find a specific example. But things don't look so good if you look at the negated universal theorems. does not follow that HA can find a specific counterexample to a negated universal theorem. And so indeed, this is what happens with the non-constructive existence theorems. They all get somehow converted into these negated universal. So he's worried that somehow this is still not really constructive enough, and that one might desire to bring something more explicit here to light. That's the initial worry. This is not a knockdown objection. He has another objection, which I think is deeper. So this is some kind of worry that there may be some non-constructive element in hating arithmetic, but Gödel thinks he can actually put his finger on what that non-constructive element is. He's very suspicious of the notion of proof that occurs in the explanation of the intuitionistic connectives. And yeah, so this is in section 2 of the handout. This objection about unformalizability. His worry basically is that the notion of proof. In the explanation of the intuitionistic connectives, we don't talk about truth. Instead, we say things like proof of A and B is a pair consisting of a proof of A and a proof of B, or a proof of A implies B is a construction which transforms any proof of A into a proof of B. But this notion of proof has a very strange modal logic. That's Gödel's worry. And the modal logic is somehow essentially S4 for this notion of proof. There's somehow a natural correspondence between S4 modal logic and this notion of proof. But this means that the notion of proof occurring in the proof explanation cannot be understood as provability in any formal system. And Gödel finds this deeply disturbing. Even if I restrict myself to intuitionistic logic applied in a definite mathematical context, say I'm just looking at arithmetic, I'm just looking at HA, and I have these intuitionistic logical constants occurring in HA, and I ask myself, well, what are the proofs you need to give the proof explanation just for HA? These cannot be proofs in HA or ZFC or in any formal theory, because the modal logic is wrong. For a formalized provability predicate, you would have the Lörbachs, and this just clashes very badly with S4. It completely trivializes. So he thinks that somehow this notion of proof that the intuitionists are working with is not really as clear or constructive as one might desire. Okay, yeah. Does that make some kind of sense?
Yeah, but this argument I do not quite follow, because if you add this as a rule, because isn't this Markov principle? If you add it as a rule, like
Which one?
the lower one.
The second one.
The second one. Isn't what does Markov principle say? It says something like if
It says for existential, not negation of universal quantification. It is intuitionistically different.
But there should be something constructive here. If you have a proof that not for all XA, then you an A is quantifying free, right? It's decidable.
Mhm.
Then you just enumerate the not A's and you have a procedure, you have an effective procedure.
Yeah, it is Markov. Yeah, it is Markov rule.
Yeah, right.
Yeah.
So this feels very constructive. So why do not add this rule to HA and then instead work with HA plus Markov's rule?
So there is indeed some kind of deep connection here that the Dialectica translation automatically validates Markov's principle. And actually, even if you extend hating arithmetic to finite types, it validates Markov's principle in all the finite types, I think. Or maybe that's sorry. It does validate it for all types, but for quantify a free matrix. So somehow there is a deep connection with Markov's principle here. Okay, so there's some kind of motivation he has here. Maybe you are not necessarily convinced by these arguments against intuitionism, but let me say what Gödel's positive proposal is, and I think there is something quite attractive and natural about the positive proposal. Gödel thinks that if we really want to be completely sure that we have avoided the non-constructive notion of existence, then what we should do is work in a quantifier-free theory with decidable primitives. So on the second page of the handout, I have a quotation here. Gödel says, let me call a system strictly constructive or finitistic if it satisfies these three requirements. Firstly, the relations and functions must be decidable and calculable. Secondly, no existential quantifiers at all. And thirdly, no propositional operations applied to universal propositions. So if you're working in this kind of system, no existential quantifiers at all, no negated universal quantifiers either, then these kinds of worries cannot arise. You cannot even express a non-constructive existence claim somehow. The only way you can make an existence claim is by just exhibiting the term that's supposed to exist. So Gödel thinks it is an interesting project to see how far mathematics developed in this way, where one is being completely explicit at every single step. And somehow he sees a connection between this and Hilbert's finitism, or Hilbert's finitistic mathematics. He thinks it's somehow very much this. Okay, let me pause there. Any comments or questions at this stage?
I don't know, maybe going to be back to this claim about probability in BHK can be probability in any form of theory. I mean, I guess it depends on how precise. I mean, it's indeed if you can start to formalize BHKs through the lens of model logic, then I guess it is the case. But I mean, there's kind of different views of how you can kind of formalize BHK. I don't know. For example, if you look at modified limit realizability, right? So basically, variant realizability, where you also demand so that you realize it is a pair. Kind of doing realism. Once that kind of through, in say, for example, in a chain, verifying that realizing it works, and like this perfectly works. Right? This is kind of it's okay. It's I mean, it's kind of well, of course, maybe because you kind of you set up like in this kind of realizability for HA using HA itself, but
yeah, I think from Gödel's point of view, this would not be a satisfying explanation because you're still having you still have the quantificational logic.
This is I don't know if you do that. I'm simply saying that I don't think like this saying that like somehow like BHK cannot be dealt with using by using as notion of proof notions of proofs in some real theory. Yeah, I don't think it's true. It's true only if you kind of formalize BHK in terms of like probability trading. If you kind of dealing with kind of let's say more like if you think about this say assertions like more like witnessed assertions.
I see your point.
Then like it actually can be.
Yeah, I'll have to think more about this. Maybe we should discuss this. No, he is certainly thinking that somehow the notion of proof that occurs in the BHK explanation, he wants it to really be, I mean, it should be a proof. There should be rules of, what are the means of proof that are allowed in such a proof. And so he seems to want it to be possible to just write down what are the means of proof. So you should get a formal system to do the proofs and. I'm not.
No, but I simply was saying that
Yeah.
at least like I mean you can treat like realizability. I think probably a bit close thing would be like modified realizability uses where you also supply proofs in your realizers. That's basically an implementation of PHP.
Yeah. Okay, I should think more about this option. Yeah.
Anyway, no, I mean, like, of course, it's kind of circular, right? So you kind of, you kind of just define essentially a change using HA. So I am not sure that much of gain here from like this foundational perspective. Okay, like, I guess, of course, amplified realizability it has a lot of technical merit kind of to proving some other results, but
I mean, somehow the worry is you still need to give some explanation of the meaning of the intuitionistic connectives.
Yeah, no.
So where is that going to come from? It may be worth mentioning as well here that my understanding is at the time when the double negation translation first appeared, it came as a surprise that hating arithmetic was so powerful that it could interpret PA. This was surprising. People thought if you gave up the law of the excluded middle, it should really limit the amount of mathematics that you were able to do. And it was a pretty big surprise that, in fact, by a quite simple syntactic translation that you can somehow recover piano arithmetic. So maybe now we are very used to this fact, but I think that in Gödel's time, this really was a surprise, and that somehow it was natural to be suspicious that that the intuitionistic explanation of their logic was somehow tacitly built in too much, more than their philosophical standpoint really was supposed to let them have. Okay. Well, we should keep moving, I think. So, yeah. So this is the kind of reduction that Gödel wants to give. And the main topic of that I wish to discuss is this objection that everyone raises against the reduction. So for this, we'll need to see the reductive system T, and we'll look at Gödel's definition of computable function of finite type and see why this is supposed to bring the quantificational logic right there. So yeah, and just to finish the end of the introductory spiel, the mysterious thing here is that Gödel was well aware of the circularity objection, at least as I read him. And he was adamant that there was actually no circularity here. He explicitly addresses the matter in a page-long footnote, which we'll meet later, which, however, nobody has been able to understand what he's doing in this footnote. And this is where I got fascinated with this problem. Of course, Gödel is allowed to just be wrong. Here, there was a real gap. Nobody understands what he's doing in this footnote, and I think it is worth trying to get to the bottom of this mystery. So, plan for the rest of this talk.
What's the English word? Adamant?
Adamant, insistent. He was, yeah. So we've already discussed why Gödel thought that some kind of foundational reduction was necessary or desirable. So for the rest of the talk, I'll present system T, explain the circularity objection, and then I'm going to reconstruct this footnote and try to defend Gödel. I think Gödel was right. He does have a way of getting rid of the quantificational logic, but the foundations of theory T end up being stranger than meets the eye. And the way that he does it, to foreshadow, is he brings in a new modal operator for what he calls reductive provability. This notion of reductive provability is somehow inspired by Leibniz's notion of analyticity. Okay. So, any comments or questions at this stage? Okay, let's move on to section 3, and now I will finally show you some details of the system 3. Let's see. Yeah. So we are working in a simply typed language. The type structure of T is just you have a single basic type for natural numbers, and then you have function types built from that. Gödel sets it up so that you have k-ary function types as primitive for every natural number k. So we have basic type n, and then I'm going to write function types like this. F1 through alpha k and beta types. Then you have this type for functions from this. We don't actually have product types in Gödel setup, so my notation is slightly bad, but I think it's easier to read than this notation. Okay, so this is the type structure. And Gödel intends that these types, a function of this type is supposed to be a computable function in a very special and idiosyncratic sense of computable, which I'll define at the end of this section. It's the definition of Gödel's definition of computable here, which is the source of the whole entire objection. So we're not thinking of Turing computability. This is some higher type notion of computability here. Okay. The language of T. Yeah, there is some complicated definition. Definition by simultaneous recursion, both the signature and the terms of T. So this is the 6-part monstrosity here. Maybe before explaining what's going on here, let me say where we're going. The formulas of T. I'll do the formulas first and I'll come back to the term. The formulas of T are going to be Boolean combinations of equations between terms of equal type. So Boolean combinations of equations between terms of and we have variables here. We have been quantifier free, but we can still have free variables. And these terms are going to be built up from variables and constants function application. So the terms are built up in this quite straightforward way. The slight complication is that Gödel has lots and lots of constants. And sometimes he wants to form new constants on the basis of previously formed terms. So now let's look at the 6-part thing. We have three primitive kinds of terms. We have variables. 0 is a term, successor is a term for the system of appropriate types. And then we have application, allowing us to form terms by applying them to previously formed terms of appropriate type. And then we have these principles of explicit definition and recursive definition. These are rules for defining new constants. Explicit definition corresponds to lambda abstraction. So if I have a previously formed term, T0, containing at most the variables x1 through xk, then I can define a new constant C by setting its values equal to, whatever T0 is telling you to do with the string. So this is essentially lambda abstraction, although it has a bit more of the flavor of combinatory logic, because we don't really have a lambda operator. We're just defining somehow we're defining each individual instance of combinatory completeness that you might ever want to have. And then Gödel has recursive definition. This is primitive recursion generalized to finite types. So if I already have some of those terms, T1 and T2, I can define a function. Here H is going to be of type natural numbers to some type alpha by saying the value of the function at 0 is some object of type alpha. And then for successor, we just iterate, I think it was T1, okay. We just iterate some previously defined function. And you have to do it in a way that the iteration just keeps you in type alpha all the time. So, so the only means of defining functions in this system are explicit definition in this kind of iteration or primitive recursion. This means that the terms in T describe some kind of computational process where the computational process is extremely explicitly described. So it is clear that the computations always terminate in finitely many steps, because here you are just applying some finite combination of things to each other. And here you are just iterating finitely many steps. So it is somehow very clear that we are only ever dealing with well-defined procedures, and the manner of the computation is completely explicit. There's no unbounded searches or anything like this. In this sense, they feel very, very constructive indeed. And so the kinds of assertions one can make in the system T essentially have the form that two of these explicitly described calculation procedures always yield the same result, no matter what inputs they have.
It Gödel do some real mathematics in T because it feels very painful.
Yeah, we don't know whether he really works so much. It is indeed painful to work with this much explicitness. Yeah, somehow the expressions become much longer when you don't have quantifiers around. What, yeah, maybe to get a feel for what you can do. So if we didn't have these higher types, we would just be dealing with primitive recursive arithmetic. What do the higher types really buy you? One thing you can do, once you generalize primitive recursion to the higher types, now you can give a very easy definition of the Ackermann function, for example. And indeed, there's a kind of a short and slick way of defining the Schwichtenberg-Wiener hierarchy of fast-growing functions. You can define this very efficiently in system T in a quite neat and explicit way. So that somehow you, by having primitive recursion higher types, you really are getting yourself even more functions from numbers to numbers. You get something new at the lowest level. Yeah.
Can you characterize it like which ordinal or so would we be?
Yeah, so the functions the functions at the lowest types where it's just naturals to naturals are going to be exactly, so the functions definable in T of this type are going to be exactly the provably recursive functions of PA or HA. Yeah, so you get this kind of nice characterization. Yeah.
I mean, yes, in fact, this translation, they more or less established this fact, right?
It's more than
Basically, given that the translations that Steven talked about earlier, that's kind of you cannot plan HA in T. It's basically already thought was that in HA probably because the function is divisible in T, then yeah, and other way around, it's a very well-known fact that you can. It's an embedding in another direction of T in HA. Okay, so it's basically but perhaps you want to talk about it at some point anyway.
About
About the part where how T embeds into HA. Of course, you can give it kind of alternative, kind of alternative justification, but perhaps like it's also we want to talk about like more usual models of system T.
Yeah, I was planning only to sketch these a bit later because I think we have enough other things to discuss.
Okay.
Okay. And yeah, I should have said also that we have equality as the sole predicate in T. I guess this follows from what I said. Yeah.
so one equality, not for every type.
Yeah, so you can think of it as equality for every type. Yeah, the equations have to be between terms of equal type. Yeah. Okay. Maybe now it's time to look at the deductive system for T, which you have on page 3 of the handout. So we have axioms for classical propositional logic, axioms for equality, axioms for successor. These are all somehow just the kind of standard. Number 4 is a rule of substitution from phi of x and for phi of t. So principal axiom groups 1, 2, and 4 together are sometimes called quantifier-free classical logic. This is the same logical framework that you find for primitive recursive arithmetic. And then I'll come back to 5 and 6 is the induction for all formulas in this quantifier-free language. So 3 and 6 are giving us a little bit of arithmetical structure for our system. And then we have the defining equations, all of these constants that we introduced by explicit definition and recursive definition. And that's it. So it really is just a kind of generalization of primitive recursive arithmetic to finite types. Yeah. There are many variations one can consider. I've given the definitions following Gödel's own setup very closely. Nowadays, it's much more common to set up the system using combinators or lambda calculus. And I'm sticking to Gödel's presentation because for the historical purposes, it's somehow important to stay quite close to what he's doing, and it actually will make some of the arguments later a little bit slicker. If you set it up Gödel's way with all these constants. So setting it up with these schemes for introducing lots of new constants is somehow analogous to presentations of primitive recursive arithmetic, where you have a separate function symbol for every single primitive recursive function, and you just keep introducing lots of new function symbols by the scheme of primitive recursion. It actually has the same structure. You're introducing new function symbols on the basis of previously defined terms and functions. So, okay, so now remember, what was the point of the system? Gödel wants it to be free, and he wants the primitive notions to be decidable. I won't focus so much on decidability. It looks all very quantifier free and fine, but now we finally come to the definition of computable function of finite type. I mean, if you want to view this as a meaningful system, you have to say something about what these function types mean. So far, they've just been built into the syntax as these kind of syntactic labels, but what does it actually mean to be a computable function of some type? So here we get this definition here. The concept computable function of type T is defined as follows. The computable functions of type 0 are the natural numbers. If the concept's computable function of types T0, T1 through Tk have already been defined, then the computable function type T1 up to Tk to T0 is defined to be a well-defined mathematical procedure which can be applied to any k-tuple of computable functions of types T1 through Tk and yields a computable function of type T0 as a result, and for which, moreover, this general fact is constructively evident. This is somewhat indigestible, but we'll try and unpack it. The phrase well-defined mathematical procedure is to be accepted as having a clear meaning without any further explanation. The functions occurring in this hierarchy are called computable functions of finite type of the natural numbers. Okay, so let us try and see what is problematic about this definition. This is now section 4 on the handout. I'm going to skip the quotes where I have a couple of quotes from Troelstra and Tate complaining about this, but let's just skip ahead to the objection. So, yeah. So let us look at the special case of a unary computable function. What does it mean saying f is a computable function type alpha beta? Yeah, so I have a slightly simplified version on the hand. It's going to be f is so firstly, f is a well-defined mathematical procedure that can be applied to any object of type alpha to yield an object of type beta. And secondly, it's constructively evident that the first clause holds. Gödel never defines this notion of constructively evident. Okay, what is the problem? The problem is with any in the first clause. That is going to give us quantificational complexity. So, for simplicity, I want to forget about the second clause. We have the second clause about constructively evident. Let's drop that for now and look at what happens if you don't have that clause at all. And then let's look at the special case where the type is this one. Yeah. Then what are we saying? F is computable of this type here means F is a well-defined mathematical procedure that takes any well-defined mathematical procedure that takes a number to a number. And if you sort of symbolize this, you end up with this kind of thing on the handout. And you can now see you've got this universal quantifier occurring in the antecedent of an implication, and you're going to start getting, we have propositional operations being applied to universal quantifiers. It seems like this just clearly violates Gödel's own idea of strict constructivity.
That's actually maybe going to note here. So in fact, I think you basically kind of take you drop item 2 its definition, and
Yeah.
take item 1, and then you kind of read mathematical procedure as an algorithm or Turing machines, and basically what you get is what's known as HRO.
Yes.
So HRO, entirely recursive preparations, kind of. Anyway, this kind of a model of functions of high types, and then give us how you embed system T in HA. So basically, you precisely do the definition, like here, interpreting these mathematical procedures, index per Turing function, something like that.
Right.
Yeah. Yeah, maybe it's worth digressing to talk about this model since it's a bit more concrete and gives us something to compare this with. Yeah, so with the hereditarily recursive operations, we would say the computable functions of type yeah, I mean, just so you know, I'll just give some examples. The computable functions of type n to n are going to just be total recursive functions in Turing's sense, just total computable functions. And then if I go to a higher level, like this one, I want to say hereditarily recursive operation of this type is going to be a partial computable function, so it has to be total on the codes of these ones. So it has to be defined on all of the Gödel codes of the total recursive functions from n to n. And then you go up and up like this. So you're only dealing with partial recursive functions operating on Gödel codes of other things, but it has to be like total on the objects of appropriate type.
When was this introduced? HRO and by whom?
I don't know when it was first introduced. Gödel does talk about it in a footnote to the 1972 version of his paper. I guess it was around earlier, but I don't know the history there. Yeah. Yeah, many details about this model are given in Troelstra's epic 1973 book that has everything in the world. Yeah. Yeah, so if one tries to interpret T in this way, the issue is that to describe the model, the predicate saying that, for example, something is a computable function of this type, they grow in arithmetical complexity. Because at every step you have to ask about, is it defined on all of the total things from the previous layer? And totality is giving us a quantificational complexity. So it gets worse and worse as you go up. Yeah.
It seems that the quantification still is a bit more controlled because it's only in certain forms that you have it here, or you get probably in HA all kinds of quantification, because it seems that you only have it like in nestings of arrows and things like that.
Yeah, that's true. It does mean that you only have to deal with the predicates saying that something is a computable function of this type. It's somehow where all of the quantificational logic is. So yeah, Troelstra says about this. He thinks there is some reductive gain, though it is not clear cut. We think it falls short of Gödel's aims. So Troelstra comes to, I think, a similar conclusion to you, that it's maybe not a complete it's maybe not a complete waste of time to do this, but yeah. Okay, so sorry, got some wind damage to the structure of the standout. Here we go. Okay. Yeah. So we dropped the second clause. here. So there's a question, what happens if we put the second clause back in? Does it help at all? Prima facie, the answer is no, because Gödel's definition of computable of type alpha theta is that it's a conjunction of these two clauses, and it seems like adding another conjunct is just going to sort of add more stuff everywhere, but without removing any of these nestings of positional operations and quantifiers. Looks like it only can make things worse at face value. So what's going on here? Well, I mean, he never defines constructively evident, so clearly this is where we need to press a little more. Later, he says we should replace constructively evident with this more precise notion of reductively provable. And this is what we're now going to turn to. This is what footnote H is all about. Trying to come up with some notion here that can save us. Okay, let's see. Yeah, somehow we are not doing too badly for time, so maybe I'll pause. Any questions or comments at this stage? Okay. Yeah. All right, so let's move on to section 5 and try and figure out what reductive provability is supposed to do for us here. I have quoted much of footnote H. I don't recommend actually trying to read this or absorb it right now, but I'm just going to draw out a couple of points, and the rest is just there so that you have it if you wish to look at it. So Gödel says reductive proof, this is under number 1 of the quote. Reductive proof is roughly defined by the fact that the chain of definitions of the concepts occurring in the theorem, together with certain axioms about the primitive terms, forms by itself a proof. Okay, this is somewhat opaque, but what I think the idea is a reductive proof is supposed to be a proof that consists mainly of just unpacking definitions in the statement to be proved. A reductive proof is a chain of definitions. What is allowed in such proof is a lot of use of definitions. What is not allowed in such a proof is serious logical reason. We don't just want to start using modus ponens willy-nilly or something. It should just be unwinding definitions. Okay. Secondly, Gödel says reductively provable is a decidable property. This is the second bolded thing. Yeah, this will be important. I mean, in some sense, it has to be decidable, or it would not be strictly constructive for him. So this is another curious feature. And then third thing that I want to draw out is he says, because these proofs, that is, reductive proofs, are uniquely determined by the theorems, quantifications over any proof can be avoided. Okay, what is this about? Here, somehow the thought is, if reductively provable means there exists a reductive proof, then you've just brought the quantifiers back in again. The notion of reductively provable should not just mean there exists a reductive. I mean, you cannot just do some kind of unbounded search for a reductive proof. That would be bad. But I think somehow implicit in this idea of the reductive proofs being uniquely determined by the theorems is something stronger, that we actually have a way. If you give me a statement, I can check whether or not it's reductively provable. I have some kind of procedure for checking the definitions occurring in it to see whether they form a reductive proof or not. This is somehow the idea. Okay, but how is this supposed to help with the circularity objection? Okay, well, so yeah.
Also the case that for given a sentence, it should have at most what?
I think this is what he's saying, yeah. If something is reductively provable, it has a unique proof. So we are dealing with a strange, very restricted notion of provability. Yeah. And when we apply this notion of provability in the definition of computable function of finite type, we're restricting ourselves to considering computable functions for which we have a reductive proof that it is computable. In other words, that it takes arguments of appropriate type to an output of appropriate type. Yeah. So we are looking at well, okay, let me keep going and I'll try and say how this comes together. what I think is going on here. Okay, the next step will not be evident without, digging through a bunch more things that Gödel says in the archives about this and trying to piece together some kind of story. So I'm going to tell you the story that I have pieced together from this. But I don't think it should be obvious that this is really what Gödel is saying here, but this is what I think he's saying. Well, what I think one has to do, think of reductive provability as a new modal operator. And let us assume that this modality is factor, in the sense that we have this principle box P and P. We need this principle, or I think there is no hope of getting out of this problem. We need this principle because then you can think of the definition of computable function of type after beta. It was a conjunction of two clauses, but you can think of it as really consisting just of the second clause, because the first clause will just be implied by the second. So it will be equivalent to just the second clause alone. And if furthermore, this modality is decidable, then now we get something good. So on the handout, I have the same example from before, unpacking the definition of computable function of type, that's that. But if reductive provability works like a factor modality, then at every step, the quantifiers are being shielded by the boxes. And if the box is decidable, then the field actually does something for us. It shows that you weren't really using the power of quantificational logic, because you have some other way of thinking about these statements. You can just check the definitions. I think this is the strategy Gödel wants. Also, there is a quotation here that from the archives. Gödel says, for also, the statement that something is reductively provable means that a certain procedure of checking the chain of definitions of the concepts yields a certain result. So here he says a bit more explicitly the thing I was trying to draw out from that. I think this is the general plan. Okay, many questions remain though. What actually can occur in a reductive proof? What do the reductive proofs look like? And how can we see if these things are decidable? So let's see. Yeah, okay. I think I want to only take 10 more minutes if I can here. I actually don't think that makes it possible to get very far. Let's see how far we can. To reconstruct this notion, in the footnote, part of the footnote which I did not read, Gödel describes the system T prime. T prime is essentially what you get if you make explicit this definition of computable function of finite type, and you write it into the system T itself. In T, the types only occur as these kinds of syntactic labels, just like any other simply typed language. The types are not defined in any meaningful way in system T. But Gödel is wanting to think of the types in this meaningful way, so we should spell out what they mean. And if you do this, you get system T prime. So T is supposed to be easily interpretable in T prime, where we are just making explicit what the types really range of. My plan for reconstructing the notion of reductive provability is to guess what system T prime has to be, and guess what the interpretation is supposed to be, and then reverse engineer what do reductive proofs have to be to get an interpretation of T in this system. In other words, so to do this, what one really has to do is think T prime is going to be T prime is going to be a single sorted system where we have a bunch of predicates saying P is a computable function of type alpha, meaning that it really does take the arguments and do the right thing with them. In system T prime, you're always having to check whether terms which purport to have certain type really do have the type that they purport to have, but they really have the behavior this to have. So we need these predicates that allow us to reason about these terms. So, yeah, and then these predicates are going to be defined the way that Gödel desires. So if we have a function type alpha beta, then we define these in terms of reductive probability. Hello, and is there any spare handout for this? Okay, yeah. So what I have written down here is nothing other. What I've written down here is nothing other than Gödel's definition of computable of type alpha to beta, but just reformulated with a modal operator for reductively provable. And again, making use of this assumption that we only have to deal with the second clause because it absorbs the first clause. Yeah. So this will be one of the new axioms that we put into T prime. And then the question is if we
Is that really an implication or a logical implication?
Yes. So in both T and T prime, we do want to have the classical propositional connectives here. So this will be classical implication. Yeah. Yeah.
I guess kind of the point here with this, you really want to deal with right. So you really want to deal with decidable formulas, right?
Yes.
So in that sense, like there are no different things. Classical and deterministic implications for decidable formulas.
Yeah. So in order for the use of classical propositional logic to be justified, Gödel is thinking that all of the atomic formulas are decidable. And somehow the decision procedure is just, well, you know what calculation procedure, all of the closed atomic formulas are decidable. And the idea is, well, you know what these calculation procedures mean, so just carry them out. That's to decide them. And so he thinks it's not really that big of a deal to have classical. Okay. Yeah, so sorry, I don't know if I've made this very clear, but the idea of T prime is just replace all of the, so in T we might have had type superscripts on all of the variables. You could have had type superscripts on the terms too. Everything is rigidly typed in system T so that we have some syntactic type. In system T prime, we want to make all of these type attributions explicit using these new predicates, and then we want to define the types with this modal operator, and then we want to see what does it take now to interpret T if you define the types. Okay, you can find the system T prime now on page 6 of the handout, and then the language is defined on pages 5 and 6. So to be a little more precise now, we're in a single sorted language. We have variables which are supposed to range over both numbers and well-defined mathematical procedures. Remember, Gödel says he wants to take this as primitive and well understood without further explanation. Okay, so we have some domain here. The signature of T prime has the same constants as T. These new predicate symbols for computable of type alpha. We now have application functions of every finite arity. And we also need this new thing for dealing with definedness. So unfortunately, the issue when you move to a single sorted setting is that now it becomes possible to say things like successor applied to successor, which intuitively are not very meaningful. So you now have to say, well, this term in the system is not really defined, even though this was defined and this was defined. But you don't want to say that you can always meaningfully apply well-defined things and still get a well-defined. So what you want to really do here is work in a so-called logic of partial terms, or negative free logic. This is kind of an annoying technical complication, but it actually doesn't make that much of a difference to any of the arguments that one wants to make.
All right, so you also want to consider this, that formula asserting that something that the value of the curve is defined and decided.
Yes, you do want to consider this. You want to consider all of the primitive notions in T prime as decidable. So those primitives, all of the primitive formulas. So you want to say closed equations have to be decidable. You want to say these things have to be decidable. And you want to say these things, the closed terms, have to be decidable. The idea is that if you give me a term in this system, yeah, somehow it should be clear whether it is defined, because if it's defined, you should have given the definition of it. Yeah, maybe, I mean, I can say something.
All these closed terms.
Yeah, closed terms. What we will assume is that all of the constants and variables are defined, and then we have some ways of reasoning about the we have some ways of reasoning about when you can get a defined thing out of previously defined things. Yeah, I have not thought too deeply about this question of whether this assumption is really justified that this is decidable, but I think it is somehow convincing if you think that you're dealing with, a given term.
Yeah. No, I mean, I think it's very much depends on what do you think your kind of terms are, right? So if you,
Yeah.
so I mean, indeed, if you kind of think that you basically your domain consists of terms of system T, then this is indeed kind of very natural assumption because there really the term is defined with it's five like checking conditions, right?
Yeah.
So this is and this clearly can be like this. I'm not problematic to say that this is simple, but then like there's about equality, right? So because your domain is really domain built on this terms, then right. So then you kind of essentially you kind of have to presuppose that you actually can essentially perform normalization, right? Which what we boil down.
I think this is a very perceptive objection. I do want to say ultimately, for the way that I'm going to define reductive provability, we are only going to be talking about computable functions that are actually definable in T. So that in some sense we are looking at a kind of term model here, the way that I want to set it up. Gödel has some strange claim that somehow you should be able to do it for HRO as well. I have no idea how to make sense of this. But yeah, so I want to look at the narrowest possible. I want to look at the interpretation of T where you have the fewest possible computable functions. But then the issue you just brought up about equality. I think what Gödel should say is it doesn't really presuppose normalization if you're thinking about the functions occurring in T as meaningful procedures.
But like, no, but then how, what equality here means, right? So because it's not really seems it's like it's not that they can exactly identify stars, probably, right? But like it's very identical. And then when you want to say that values are identical, you kind of to be able to perform the computation until you essentially reach some point, right? Because how I don't know, maybe you have some other kind of comparison criteria in mind, but it's not going to be better.
Yeah, this is a quite subtle issue. Gödel claims that he's dealing with intentional equality at higher types, but then he never explains how to define intentional equality. And I think that
No. That's basically what I'm saying. And yes, because special equality would indeed be means that you kind of try to substitute arguments.
Yeah.
And then like you kind of like the same thing. You kind of try to reduce equality in higher types to equality on type of proof. Okay, this is
Yeah.
but the frictional one, it's kind of typically means that some sort of like normal tension. So when you indeed try to so-called normalize like this expression, basically normalize version of the expression, I'd say something like that, because like you, it certainly wouldn't work if you simply compare them graphically as they are.
Yes, that's certainly true. Gödel is thinking that um, uh, you don't need a normalization procedure. You don't need a proof of normalization. Maybe that's the thing I should say.
No,
Yeah. You can think of it as normalization if you like, but he thinks that you don't need a proof of normalization. Because if you needed a proof of normalization, it would destroy the alleged reduction.
especially by kind of sick. You go to me.
Yeah. So maybe what I should say is he just thinks that somehow for the particular procedures definable in T, it is obvious without proof that the computation terminates. That is supposed to be the gain here, just in the way that, you know, if I look at the definition of the exponential function, you know, you know I'm defining the exponential function by these equations. It is somehow obvious that exponentiation is well defined and that it will always give you a natural number when you put in two natural numbers. You don't need a proof of normalization or something. He thinks we understand this mode of definition. Yeah.
Okay. No, but right. I mean, I thought that you however, so my concern was about this kind of essentially kind of claims of the stability of various properties here, right? And right, if you kind of start to ask about like arbitrary qualities, okay, you kind of basically the way how you uh, can check the two terms have equal values if you can perform the computation.
Yeah.
This kind of two. Okay, the values are the same.
Yes, one does have to think of it this way. That somehow in the end you imagine, yeah, you carry through the calculation, you just check
No,
out.
this is not normalization. Right?
Yeah.
Normalization is precisely performing computation to them, like that's the same.
Yeah, I mean, it is. It is in some sense the same. Yeah, it's hard to say precisely the sense in which it is and isn't the same. Um, Gödel thinks it makes a difference if you're conceiving of the procedures as meaningful procedures versus as like just some meaningless pieces of syntax to which we blindly apply reduction rules.
Yeah, no, but I think it's actually probably like it's more or less the same as what you probably will say that the probability is, right? So because probably like what you want to say that the probability is that you just start to unpack the definition. That this you essentially kind of try to kind of eliminate basically apples institutions. And this is basically what is normalization procedure. It's kind of
I don't think this is what
okay,
reductive
okay,
I think it is a natural reading, but I think this is not what Gödel
okay.
has in mind.
Okay. Okay, anyway, maybe we'll go further. I saw that.
Yeah, let's keep going. And see. Okay, I may have to move a little more quickly here. So on page 6, you get the deductive system for T prime. Does it? Okay, so we have these atomic formulas. Yeah, okay, hopefully the system is kind of clear. So the axioms 1 prime through 6 prime are just copied from T, except that the type attributions are now being handled by these explicit predicates. And also there's this slight wrinkle about the partially defined things, so that we have to change the logic axioms very slightly. But the new stuff, axiom group 9 prime is some kind of bookkeeping for handling definedness. I don't want to dwell on it. 8 prime is this principle where you just write down the definitions of the types. 7 prime is the interesting part. These are the only two things that you need to add to get an easy interpretation of T and T prime. It does seem necessary to add them. So the first principle says that, if phi is reductively provable, then phi. In other words, reductive proofs establish their conclusions. The second principle says if you have a reductive proof of phi, you can infer that phi is reductively provable. You can infer box phi. So this is, in modal logic, this is kind of like T in necessitation, sort of. There's a lot to say about these two principles. They are kind of a refinement of principles that you would expect to govern the concept of absolute provability or provability by any means whatsoever. Version is inconsistent, but this one you'll see is quite plausibly consistent because it's such a narrow notion. Okay, so let's see. What can we say? Right, so if you now try to interpret T in this system, I still have not told you what a reductive proof is. It drops out from the interpretation. So if you interpret T in T prime in the natural way, where you just translate each formula phi of T by the formula where you add the predicates out the front, saying that all the variables occurring in phi have the text that they're supposed to have. So this is at the bottom of page 6. You translate it in this way of just making more explicit what each formula of T is saying. Then the verification is generally quite straightforward. I intended to demonstrate. Right, so yeah, the main non-trivial thing is showing that terms have the types they're supposed to have. So we have theorem 1, which says T is a term of T purportedly of type alpha, whose variables are exactly Z1 through Zk. Then T prime has to prove reductively that as long as Z1 through Zk really do denote computable functions of the right types, then so does T. So this is the thing that you need to check. The proof is just by induction on the term T. The induction has a slightly weird structure because of the weird definition of the language of T. So you have to follow Gödel's definition, and you get these inductions. I wanted to go through the proofs for application and explicit definitions to show you where 7 prime A and 7 prime B are used, but I feel that somehow we're getting close to the end of the time allotted, and I don't want to. Yeah, it's too bad because I feel that you really need to see the argument to get a sense of how it's being used. Maybe I'll just skip to the punchline, and then we can officially end. And then, if people want to see more, then they can ask me questions. My proposal for at the bottom of page 7, we get reductive proofs finally defined. It turns out that the only proofs which have to be reductive to get this interpretation to go through is the axioms of groups 1 prime to 3 prime, also weakenings of these axioms so we need proofs of this form here. Then we need the axioms of group 5 prime as well. Okay, so 1 prime through 3 prime were propositional logic, equality, and successor. They are just some kind of axioms regarding primitive notions here. 5 prime was the definitions of the constant, and we definitely want the definitions to be reductive proofs because reductive proofs are supposed to be made up of definitions. And then the only other proofs that you need to be reductive are the proofs of each instance of this theorem 1, saying that each term has the type it's supposed to. The use of quantificational logic gets divided up into each use of one of the lemmas. So there'll be a little bit of propositional logic within each lemma, but But you can't use propositional logic willy-nilly. Yeah.
Yes, I don't understand the definition. So, okay, so you're saying that so you unify these notions of reductive proof,
Yes.
and then you kind of listing things that are reductive proofs.
Yes.
But the things are kind of okay. If you don't have any kind of form, like that.
So I propose to just say reductive proofs are only the things built up in this way. But
No, but
yeah. I don't write this. What do you mean no closure proof?
no. You kind of do like it's not really an institutional notion, right? So it's you basically say that this thing is reductive to this, and like there's no ways of reducing that.
Yeah, sorry, I didn't explicitly write that down. You can think of it as an inductive definition. Say we are doing this as an inductive definition of reductive proof.
No, but like where is the induction step, right? Because okay, you say that okay, yeah, I see so actions are reductive proofs. Okay, then you say that small derivations where you weaken this actions, this also fine. Then okay, there's also some other actions are also right. And finally, yeah, okay, you can fix this for 0, 1. That else everything.
Our proofs. Sorry. So you have to specify specific proofs of like a specific proof template for each limb. It has to be single. I need to demonstrate this, or it will not be clear at all. I'm sorry.
Okay, okay, you have your serial, it's fine, right? So then you can just verify. But what about lengths? Because it's such a okay, I checked. It is kind of statement false.
So the conclusion of each lemma is going to be somehow a special case of theorem one, and then you prove theorem one just by applying the lemmas over and over.
Okay.
Yeah.
Oh, right. Yeah.
Okay, so then, yeah, there's some more things. Let me see that. I think I'll at least do application so that you can see one example of how this lemma is supposed to work. I don't think I can do both, but I'll do application and then we can call it a day. What does the application lemma say? It says let T be a term of T of type alpha 1 through alpha k to beta, and the S1 and SK be terms of T of types alpha 1 through alpha k respectively, and they have some variables occurring in them. Given reductive proofs that each of the terms T, S1 through SK have the correct types, that they are computable functions for the proof, we can exhibit a reductive proof that T applied to S1 through SK also has the correct type. Let me simplify and set k equals to 1 and say there's one free variable in each term just to sort of give a picture. So we're supposing we have reductive proofs of the statements we want to show that T applied to this is a computable function. Is right. Okay, so how can we do this? Okay, so unpacking the definition of computable of type alpha beta, we can infer from one, we have let's say this is what it means to say T is computable of type alpha beta. Now we need factivity, specific time A. And a bit of logic as well here. So we had to use a little bit of propositional logic to get. So box P implies P, and then you put this together. And now our substitution. Okay, with substitution, because of the definedness thing, there's a slight hitch that you get something like this. If S is defined, then now you can substitute S for F. But by the logical setup, if S is computable type alpha, then it is defined. This is built into the logic. So then now we are basically done by two over there, I guess. Sorry. These numbers are different from these by two and logic, and also I guess finding this, then you get so it is a very short and straightforward argument. One is somehow just unpacking definitions, but you need a little bit of modus ponens to put it together. I claim this is in the spirit of what Gödel is talking about when he brings in this notion of reductive provability. And then if you look at the, so that was application. If you look at explicit definitions, so here we saw why 7' A is necessary. If you look at explicit definitions, you'll see why 7' B is necessary. That somehow one needs to be able to pass from a reductive proof to a statement something is reductively provable. Yeah, so the idea is then reductive proofs just look like carrying out these little chunks of reasoning over and over again. Yeah. Yeah, please.
So I understand Z is a variable, so you won't need a proof, so there's no box. Or you don't need a reductive proof because it's an assumption that it has type value, right? But if you combine it with substitution, then C may be substituted later, and then you will need. So why is there not a box in front of the entity C gamma of Z?
I guess I'm not completely sure I understand the question. Why is there not a box?
I mean, that was the idea, right? That we replace the typing, that we need a reductive proof of that. Of the typing that Z is of type gamma.
Yeah.
So what there you have the. So you only do the box when you have implication types, not for basic types or. Okay, so I'm not.
Sorry, I feel that I still don't understand.
Okay, so the box stands for explicit reductive proof.
Yes, yeah.
Okay, so I thought we every time now that we have a typing statement that we leaving like a proof for that.
Ah, um,
So
yeah. So if I don't know if this exactly addresses what you're saying. If you were to unpack this C gamma, if gamma was itself a function type, then this would be a statement that we have a reductive proof that there's such and such a thing as reductively provable. On the other hand, if gamma is type natural numbers, it just says Z is a natural. Is that
right, so there may be boxes.
Yeah, if you were to unpack that further, it would really be a box.
Thanks. That
Yeah. 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 Okay, I feel that we are at an hour and 20 minutes now, and this is somehow long enough. So perhaps we should call it here. Um,
Yeah, so yeah, okay, yeah. So maybe then it's still kind of return to this kind
Yeah.
of it's kind of right. So I kind of yeah, okay, right. So this is some give more what to do. So now kind of what I think is problematic. This system is then action that C alpha of T implies T is defined.
Which one?
Nine prime. So it's the second line of action group nine prime.
Okay, so let me say a little more about how defining this is supposed to work. The idea is that so this is all tangent to this margin note here if you wish to follow along. The idea is that we still want to have classical propositional logic here. So we see that atomic formulas are false if one of the arguments is undefined. So
Okay.
so when we say that, when we say this thing, or this is yeah.
Well, I mean, okay, so, anyway, my point, okay, so this is, I guess there's still a bit of a question. So how exactly you read if the strength that T is defined? Do you read it as simply it's kind of well-formed product, so you basically apply correct types to correct types? Or do you read it as the fact that like you can normalize, you can kind of proceed with full computation of T and hence normalize it?
Uh,
Which I guess if after this kind of formula, then I guess it's simply the same issue, simply push to clarify.
yeah, so I guess in this setup, we're assuming the third line of 9 prime is assuming that the primitive constants are all defined. And then our only way of really showing that anything else is defined is by showing that it's a computable function of a certain type. And the way of showing that is either by giving a reductive proof, or if it's in terms of natural number type, then you don't have to exactly give a reductive proof, but it should somehow just be a yeah.
So how do you understand? But yeah, I mean, I'm talking about like interpretation of the system, right? How is that the construction of something defined should be understood? So I find that at least I find this like intended interpretation is
Yeah.
where this so your object can so essentially a range of terms of system T.
Yeah, that would be fine. This
Yeah. Then okay, then
close to its normal form.
yeah. Then basically like T here is some sort of like this sequence of like basically you can apply like system T constants to each other, and like this is like your T. It's how you exactly read T down there.
I mean, basically, the point is that because we're in the single sorted language, you can apply anything to anything.
Sure.
So I just want to say, like, in some sense, you can think of this as saying you just have a junk object, and whenever I want to apply, if I want to apply successor to successor, then I say it's the junk object.
Right. Right. So basically,
It's like the notational.
Basically, patching. So basically, how this is actually about patching. So basically, you just check that like you success, like when you write like T applied to you, this basically means that like type key, basically the text. Nothing more than that.
I think so.
Okay, good. So then I think the problem is getting pushed to equality. Then, okay. So very precisely, it's quality, right? So we say that, right? Right, so then I guess, right, right, so the kind of a problematic part would be, what, second, question that, then I just kind of somehow I feel that somehow like you smuggle in like strong normalization to see all right, strong like a big normalization system, something like this. That's essentially presumption of this consideration. But yeah, it's can simply not really want to check out like we check from which we check that once. Yes. Okay, I would be thinking more. Well, I understand flash construction, right? It's not a big, yeah. And down, basically the goal for that here is right. So that essentially, okay, that kind of two sides, right? On one side, the other kind of like you're very again, you define like this very small class of windows, right? And then yeah, you say okay, then basically you by definition you say like term is a good term if like you kind of check this good term, but basically checking that it's a good term is just kind of essentially checking that it's a well built term of system. Nothing much to it. Alright, so this is happening on one side. But at some point you kind of start want to start to kind of actually talk about the quality of values of such terms, which kind of basically what like and like in order to me to about this, essentially you have to normalize it because otherwise like it's not clear, isn't clear what the quality means.
Yeah, I mean, I think I want to say, yeah, you have to imagine evaluating them, and evaluating them in some sense comes to normalizing them because you want the final value to be something like a normal form. You know, if I'm evaluating two expressions of type n, I want to get it down to numerals. Conceptually, I want to get it down to numerals in the end, and then numerals are the same or not, and then I can tell whether I had the same number. Yeah.
Right, and for me, like, then the problem is the following, right? So why do we believe kind of because like I think kind of what you're trying to claim is that somehow like you have this new kind of justification for system T, but how you actually can justify that this invitation by switches terminate then about can you turn it back to something like a model HRO, something like this.
Yeah.
So
This is the place where Gödel, I think, just has to say, you have to regard it as clear that the computation procedures terminate. And the reason why it's clear is because the specific computation procedures in T are so simple. It's just explicit definitions and primitive recursion. Yeah, so this is where, you know, if there's going to be some kind of epistemological gain, it has to be here. You just say, this is the thing that this is the thing that I trust. This is the thing I'm willing to rely on, that these definitions, in fact, describe finitely terminating.
Yeah, so then when I go into the sentence, what precisely you bring to the table on top of essentially saying that, like, okay, like the system T as like term system, right? It's kind of we kind of disregard this interpretation of system T, but this system, okay, because it's term system. like it's somehow obvious that this term system is result in kind of computations that do always terminate.
Yeah, the way that I set it up, it does end up looking a lot like the term model, and reductive provability ends up agreeing with just doing the syntactic type check. It gives the same results. I mean, I reverse engineered it somehow precisely to this. Yeah, so then the question is like, what more do we get over just the term model? In the term model, the way to define application, if T and S are closed terms in normal form, then T applied to S is not necessarily going to be in normal form, so you have to think of normalizing it here. I guess the way that I was just putting it is maybe not that satisfactory.
Yeah, but my technical think when you're trying to define like, what equality means for your system, like probably you will have to do the same thing.
Yeah. I mean, yeah, I guess I have to think more. The formulation I just used, that normalization is kind of obvious, is a dangerous one for me to use, because if normalization really is obvious, then you have the term model. I think Gödel was saying something a little different from that. It's not exactly that normalization is obvious. But that nonetheless, it's somehow obvious that the computation procedures terminate. So there is some kind of fine distinction there that I will have to think about. Yeah.
I think maybe it's better. Maybe discuss it later at some point. Maybe some other people have some questions.
Just before I rush off to my train, thank you very much for the talk. I really enjoyed it. Could you just say what is your part? Or your part is so T prime was already mentioned by Gödel, or and your part is the box, the explicit notional reductive
Probability.
Yeah, so Gödel sketches the idea of a system T prime, but without writing down any axioms or anything. He gives no formal detail. Everything he says about T prime is in the footnotes that I quoted. So we did not read every part of it, but if you read it, you'll see it's very, very sketchy. So my contribution was to write down some formal reconstruction of what T prime should have been, some formal construction of what rules reductive provability should be. Yeah, so this is somehow the first time anyone has an explicit analysis of what Gödel was up to here. Gödel was raising some difficult questions. Perhaps it is not ultimately satisfactory, but I think we can at least say now what he was up to. I think there are interesting questions here as well about modalities. Like I didn't go into this so much, but this kind of proof modality has it's sort of interesting that it's a restriction of these principles of absolute provability, and I think it would be interesting to see somehow how far can you maintain the principles, from a proof of P and third P, P is provable in P, and from a proof of P, infer that P is provable. I think it is interesting to see how far can principles like this be pushed. I mean, normally one thinks you're just going to run into paradox pretty quickly with this kind of thing. Gödel has, I think, here some kind of way of getting something out of this, and maybe there's a way you could get something stronger. They're so natural, there's such natural principles about proof. Yeah. Yeah. All right, you better catch your train. I don't want to keep you. Also, anybody else who needs to leave, we didn't have a break, so I feel guilty for keeping you presently.
Yeah. Well, fine. Let's say.